All right, so we've got to section 5.5, zeros of polynomial functions. So here we're identifying the factor theorem. According to the factor theorem, k is a zero of f of x if and only if x minus k is a factor of the function f of x. So let's show that x plus 2 is a factor of this polynomial x cubed minus 6x squared plus minus x plus 30. So we want to find the remaining factors and we want to use the factors to determine the zeros of the polynomial. The way that we do this is that we are going to use the factor x plus 2 and use synthetic division. So because this is x plus 2, remember this means that we get x equals negative 2. So we're going to start off with negative 2 and we're basically dividing it out of the polynomial. So here we're going to have 1, negative 6, negative 1, and 30. So we're going to bring down the 1. 1 times negative 2. Sorry. We have 1. 1 times negative 2. And then negative 6 minus 2, that's going to give us a negative 8. And negative 2 times negative 8, that gives us a positive 16. 16 and minus 1, that's going to give us a positive 15. 15 and negative 2, that gives us a negative 30. And we get a 0 as a remainder. So then we're left with our quotient will be x. Remember, we were in x cubed, so now we're x squared minus 8x plus 15. Okay. So here's the quotient. Alright, so since we just showed using synthetic division that x plus 2 is a factor, this means that we can take the original expression, x cubed minus 6x squared minus x plus 30, and it would factor to x plus 2 and x squared minus 8x plus 15, which is what we obtained from the synthetic division. We can now take this and we can factor this down. So we're going to end up with x plus 2 and then x and x. We want two numbers that multiply to 15 but add to negative 8, so that's going to give us a negative 5 and a negative 3. So now we see that these are our three factors, okay, which tells us that our zeros are going to be x plus 2 equal to 0, which is going to be negative 2, positive 5, and positive 3. And that's it. Let's take a look at the next one. So our example, consider the function f of x equals x cubed plus 5x squared minus 44x plus 60. If f of x equals 0 and x equals negative 10, for what other values of x is the function equal to 0? So we're going to go ahead and start off again with our synthetic division, because this is telling us that when x equals 10, our function is a 0. So we're going to have negative 10. And let's write out our values. Let's make sure there are no gaps. So I have 1, 5, negative 44, and 60. Negative 10 times 1, that's going to give us a negative 10. 5 and negative 10, that's a negative 5. Negative 10 and negative 5, that gives me a positive 50. 50 and negative 44, that's going to give me a positive 6. Negative 10 and 6 gives me a negative 60, and I get a 0. So it means I got a 0 as a remainder, which means it is a factor. And when I write out that quotient, we're going to end up with x squared minus 5x plus 6. And I know it's an x squared since that's an x cubed, so it's always one less. Okay, so this tells me that the polynomial x cubed plus 5x squared minus 44x plus 60 can be factored into x plus 10 and x squared minus 5x plus 6. So now we can factor this trinomial here and know that we have x and x, And so I need two numbers that multiply to 6 but add to -5. So we're going to get 2 and 3. And both of those are going to be negative. So this tells me that the zeros then are going to be -10, +2, and +3 based off of the factor form here. Okay. Excellent. All right, so hopefully that's coming together and making sense there. So let's take a look now at the rational zero theorem. So the rational zero theorem states that for the polynomial f of x, and this is what it looks like, has integer coefficients, then every rational zero of f of x of the form p over q, where p is a factor of the constant term a sub naught, and q is a factor of the leading coefficient a sub n. When the leading coefficient is 1, the possible rational zeros are the factors of the constant term. So I know this is really hard for us to digest, so let's take a look at how this goes into play. So how to? Given a polynomial function f of x, we use the rational zero theorem to find the rational zeros. So we're going to determine all factors of the constant term and all factors of the leading coefficient. So we're going to determine all possible p over q's, where p are factors of the constant term and q is the factor of the leading coefficient. And we're going to be sure to include both positive and negative candidates, and then determine which possible zero are actual zeros by evaluating the case of f of p over q. Okay, so we're just taking a look at listing all the possible zeros. Okay, so here, let's take a look at this example. So we want to list all possible zeros. And so when we're looking at this is going to give us the idea that we should probably be looking at that rational zero theorem. Okay, so we're going to look at this 2. Remember, this is our a sub n because it's the leading one. And so this is equal to 2, but this is also our q that was being defined. And our -4, this is our a sub naught, right? Which is 4, which is going to be our p. Okay. So the general form of a polynomial, remember that it's the a sub n, x to the n plus ... all the way to our constant term a sub naught, right? So this is where our p comes from. This is where sorry, I said that backwards. This is where our q comes from, and this is where our p comes from. Okay, so we need to figure out the factors of our p. So our p is 4. So what are the factors? So our factors of 4, well, that's plus or minus 1, plus or minus 2, and plus or minus 4. And that's it. Those are the only factors of 4. For q, our q value was 2. So what are the factors? That's going to be plus or minus 1 and plus or minus 2. Okay. So now what does this mean? So now that I got the factors of both our p and our q, we're really looking at now the fraction possibilities, p over q. Okay. So then we're going to get the plus or minus. We'll just add that to the front. But what are our possible combinations? Well, I could have 1 over 1, right, using this one and this one. But then I could also have 1 over 2 using this one and this one. And then what else could I have? Well, I could have, now let's start over here, 2 over 1. And then I could have 2 over 2. Okay, and now I'm over here. So then I could have 4 over 1. Or I could have 4 over 2. Okay. And those are really all the values. So let's now simplify these down. So 2 over 1, this is just the number 2. But at 2 over 2, this is 1. 4, that's 4, and then 4 over 2, this is 2. So really, what values do I really have? Okay, I have 1, 1/2, I have 2, and 4. These are our p's over q. So all possible, so let's just write it out here. All possible rational zeros are plus or minus 1, plus or minus 1/2, plus or minus 2, and plus or minus 4. Those are all the possible rational zeros that we are capable of getting from this polynomial. Okay. Use the rational zero theorem to find the rational zeros of this function. Go ahead and pause the video and try it out. Alright, so here we're going to use the rational zero theorem. So let's take a look at the leading coefficient here. We have a 2. So, alright, this is our a to the n, which is a 2, which is also our z, right? Here our 1 is our a naught, but this is also known as our p, right? So we have a 1 here. So let's take a look at all the possible factors. So we're going to have p over q. So all the possible factors of p, since p is 1, is just plus or minus 1. Since q is 2, we have plus or minus 1, and we have plus or minus 2. So when we look at p over q, what are the possible factors that we have? Well, we have plus or minus 1 over 1, and then we have plus or minus 1 over 2. So we only have 4 potential factors, right? So this equals, we have 1, plus or minus 1, and plus or minus 1/2. Okay. Alright, so all of our possible zeros really turns into 4 possibilities. We have positive 1, we have positive 1/2, we have negative 1, and we have negative 1/2. Alright, so we want to find the rational zeros of this function. Alright, so since these are our possible zeros, but that doesn't really tell us what all the zeros are. So we want to find the rational zeros. So we're trying to find the actual zeros, not just the possible zeros. So we want to make to check these zeros. We want to be able to check the zeros. One way to do this is to do synthetic division. So if we did synthetic division for all of this, so let's go ahead and start with 1. So if I plug that in, alright, here we have 2, 1, negative 4, and 1. So 1 times 2 is 2, 2 and 1, that's 3, 1 and 3 is 3, so this would give me negative 1 times 1 is negative 1, and so this is 0. So this tells me that x equals 1 is a 0, okay, for our function. I could do this for the rest of these, so we know that this one checks out. So if I did a half, for instance, plug in a half, so 2, 1, negative 4, 1. 2, half of 2 is 1. This is 2, half of 2 is 1, and then this gives me negative 3. Negative 3, this will give me negative 3 over 2, and I end up with this being negative half. And so because of that, though, this tells me that this is not, because I have a remainder, this is not a 0. So x does not equal 1/2. So now let's try a negative 1/2. I'm going to erase these. So if I try a negative half, bring down the 2, we still have 2, but now this becomes negative 1, so I'm left with 0, which is 0, negative 4. This gives me a positive 2, but again, I end up with a remainder because this will now be 3. So that means negative 1/2 is not a 0, so our halves are out. So now let's try 1. So if I plug in negative 1, so negative 1 times this gives me negative 2. 1 and negative 2 gives me negative 1, so then this gives me positive 1, and then I get a 3, a negative 3, negative 1, and this gives me a positive 3. So then I end up with another remainder. So therefore, the only possible 0 that we got was x equals 1. Okay. Because the synthetic division did not check out for the other ones. So I could also, so that's technically the long way, because the other thing that we could do is we could actually plug it in. Since we have the function here already, right, we could take the function, graph it, and see if the rest of these zeros work out, the 1/2, the negative 1, or the negative 1/2. And so if we were to do that in Desmos, let's move over to Desmos real quick. So notice that if we take our graph and we graph it out here, we can see that at f of 1, which is the value that we tested, we do have a 0. If we look at f of 1/2, which is another value that we tested, we end up with negative 0.5. F of negative 1, we end up with 4. And I think that's it right there, negative 1 and 4. And then if we look at f of negative 1/2, we end up with 3. So you can see here that, disconnect these. So just in looking at this, we can see that the only value that actually equated in a 0 was that f of 1. And so we could have plugged it back into the function to check it out. We could have checked it with synthetic division, or we could have graphed it and checked it. But we see that the only possible 0 was that 1 there. All right. Uh-oh. There it goes. Let's look at the fundamental theorem of algebra. This is another theorem that is going to come up a lot in calculus. So this is just our first exposure to it. The fundamental theorem of algebra states that if f of x is a polynomial of degree n greater than 0, f of x has at least one complex 0. Excuse me. We can use this theorem to argue that if f of x is a polynomial of degree n greater than 0 and a is a non-zero real number, f of x has exactly n linear factors. In other words, that we can factor it out this way, where all these c's are actually complex numbers. So therefore, f of x has n roots if we allow for multiplicities. So in other words, if we have a polynomial of degree 4, it's going to have 4 roots, allowing for multiplicity, right? So in this particular case, now we're even allowing to find the zeros that are complex. So let's look at this first example. Find zeros of this polynomial f of x equals 3x cubed plus 9x squared plus x plus 3. So our leading coefficient is 3. Our constant is 3, so we're going to use that the theorem we were just looking at earlier. So we have our a of n is equal to 3, which is also our q. Our a sub naught is also equals to 3. Right? So let's look at the factors. Excuse me, I have to cough. Oh, sorry about that. All right, so when we look at the factors of p, we're going to get plus or minus 1 and plus or minus 3. When we look at the factors of q, again, we get that plus or minus 1 and the plus or minus 3. So when we're looking at the factors of p over q, right, it's all those possible combinations, we're going to get plus or minus 1 over 1, plus or minus 1 over 3, and they get plus or minus 3 over 1 and plus or minus 3 over 3. Now remember that 3 over 3 is just 1, and so we really got plus or minus 1, 1/3, and 3 as our possible roots. Okay, so let's go ahead and take a look at the calculator. Right, so actually, let's break this up first. So notice that how many roots do we really have here? We're going to get negative 3, negative 1/3, and negative 1, 1, 1/3, and 3. So we're really looking at 6 possible roots. So let's go ahead and plug these in. We can plug these into the original equation, or we can look at a table of values and figure out which one of these would give us the f of x value equal to 0. So let's go ahead and navigate to Desmos. I went ahead and I inputted the function. So what we can do now here is we're going to tap on these gears. We can hit the table function and notice it just creates a table for us. So what I'm going to do is I'm actually going to add to the table function. I'm going to put in some of those values that we looked at. So we had one of the values that we had on there was 1. And so 1 gives me a 16, which tells me that that is not a 0. So then let's try negative 1. I get a positive 8. That's not a 0. Let's go ahead and try in positive 1/3. Again, not 0. So then let's try negative 1/3. Right? Again, not a 0. And so then positive 3. Yep, not a 0. And then lastly, if I look at negative 3. Negative 3 does give me that 0, and I can actually see it right here that there's that 0, right? So this is a couple different ways to check once we get those possible zeros to check them out this way. So we know that these aren't going to work out and that the correct answer is just negative 3. So now that we know that negative 3 is a 0, that just gives us one of the zeros. But based off of the fundamental theorem of algebra, we know that there are other zeros as well. So the way that we're going to do this is we're going to find it using, we're going to use synthetic division. So here's our negative 3. And then we're going to go ahead and write out the coefficients. So we have 3, 9, x, and, oops, not x, 1 and 3. Bring down the 3. 3 times 3, that gives me a negative 9. This is 0. Negative 3 times this is 0. I bring down a 1, and then I get negative 3, and this is a 0. So because this is degree 3, that means that based on synthetic division, this is going to be degree 2. So I'm going to get 3x squared plus 0x plus 1. Or in other words, this becomes 3x squared plus 1. Okay, so this is my quotient. This tells me that, going back over here to the polynomial, (3x cubed plus 9x squared plus x plus 3, that this polynomial is factored to be x plus 3. Remember, this x plus 3 came from the fact that of this negative 3 here, right? Which means that this is x plus 3 times 3x squared plus 1. And right, so here's this value. So now we have to go about and reduce this. Let's go ahead and figure out a way, how do we solve this? So here we got our 0 here. So let's set this one to 0. So I get 3x squared plus 1 equals 0. This becomes 3x squared equals negative 1, and then I end up with x squared equals negative 1 over 3. So in order to solve this, we're going to take the square root of both sides. When I take the square root of both sides, though, this really becomes plus or minus. So now I have x is equal to plus or minus the square root of negative 1/3. Which is the same thing as, we could extract that negative. You get I to the 1/3. Okay. So that tells me that our zeros then for the actual function, our final answer, our zeros are going to be negative 3, and then I'm going to have I to the 1/3 and negative I to the 1/3. All right, so that's how we find all of the zeros of this polynomial based off of the fundamental theorem of algebra. All right, let's take a look at the complex conjugate. Remember that when we're looking at complex conjugates, we do have that I squared is equal to negative 1. We did this it sounds like a while ago now. Complex conjugates, right? So according to the linear factorization theorem, a polynomial function will have the same number of factors as its degree, and each factor will be in the form of x minus c, where c is a complex number. So if the polynomial function f has real coefficients and a complex zero in the form of a plus bi, then the complex conjugate is a minus bi is also a zero. So let's take a look at this example. Find the fourth degree polynomial with real coefficients that has zeros of -3 to I, such that f of -2 is equal to 100. So we know that this is going to be, let's write down what we know. So degree 4, it's going to have real coefficients. Our zeros are going to be -3, 2, and I. And we also know that we have the value, we have the point -2, 100. So now because I is a value, what this theorem here is telling me, the complex conjugate theorem, is that if I is a value, so is its conjugate. So what's the conjugate of I? It would be -I. So that tells us that that's the fourth root right there, that -I. So let's go ahead and find the polynomial. So we're going to have f of x times a, and then we're going to have x plus 3 times x minus 2 times x minus I times x plus I. Okay. All right. So now let's go ahead and multiply these out. So if I multiply these two out, I would end up with x squared plus 3x minus 2x minus 6. And if I multiply these two out, I end up with x squared minus I x plus I x minus I squared. Okay. So let's go ahead and simplify this. Combine these two, so I get x squared plus x minus 6. And then over here, these are going to cancel out. And so I'm really left with x squared minus I squared and x squared minus I squared, well, this is just -1 times this, so I end up with x squared plus 1. All right. So now from here, we want to take the fact that we have this other point here, our -2 equals 100. So let's go ahead and plug that in. So we have 100 equals a, and then we're going to have -2 squared plus -2 minus 6, -2 squared plus 1. So -2 squared plus -2 minus 6 times -2 squared plus 1, this gives us a -20 over 100. And so we're going to divide by -20, divide by -20. So we're left with a equals -5. All right. So now let's go ahead and figure out what this polynomial is. So we have f of x is equal to -5 x squared plus x minus 6 times x squared plus 1. Let's go ahead and multiply this out. So when we multiply this out, sometimes it's easier to see it in a box. So in terms of side note and side work, just to see this multiplication work out, you'll see some people that'll write it out this way. They'll say like x squared, x, and then -6. And then they'll have x squared and 1. And so what you do is you end up multiplying them together. So you have x squared times x squared, you get x to the fourth. Here this gets an x squared. This is an x to the third. Here we have another x. And then here we have negative x squared, negative 6x squared, and then negative 6. So now what happens is that we go ahead and write them out. So we're going to have x to the fourth, which is that value, and then it would be plus x to the third, that value, and then we're left with negative 6x squared and x squared, which gives us a 5x squared, and then we're left with plus x minus 6. Alright, and so you can actually leave it like this. Feel free if you want to multiply out the 5, the negative 5, you can, but this is sufficient right here as our polynomial. Okay, if you want to multiply that 5 out, you could come a minus. Either one of those is fine. Alright, let's look at Descartes' rules for signs. Actually, how much more? Oh, this is the last one. Descartes' rules of signs. So according to Descartes' rules of signs, if we let f of x, our polynomial, be a function with real coefficients, the number of positive real zeros is either equal to the number of sign changes or less than the number of sign changes by an even integer. The number of negative real zeros is either equal to the number of sign changes or is less than the number of sign changes by an even integer, right, of this function. So let's just take a look at this in practice, right? So here we are, we're going to use this to determine the possible number of positive and negative real zeros. And so for our function f of x equals negative x to the fourth minus 3x cubed plus 6x squared minus 4x minus 12. Alright, so let's take a look at how many sign changes are occurring. So from this value to this value, there are no sign changes. But from this value to this value, there's one sign change. From here to here, there's another sign change. So that's our second sign change. And then from here to here, there's no sign change. So that's 2. So this means that there exist either 2 or 0 positive real roots. Alright, so where did these numbers come from? So it's going to be 2 because according to this rule of signs, the number of positive real zeros is either equal to the number of sign changes, which in our case was 2, or is less than the number of sign changes by an even integer, right? So if I take 2, and if it's going to be anything less than that, the next even would give us 0. So there's where we get 2 or 0 real roots there. So now let's take a look at the negative. So the negative real zeros. Okay, so we're going to let x equal negative x. Okay, we're going to plug it in. So we have f of negative x. And then we're going to get negative x to the fourth minus 3 negative x cubed plus 6 negative x squared minus 4 negative x minus 12. Okay. So now when we simplify all these signs here, we're going to get, because this is to the fourth power, this just becomes x to the fourth. This is to the third power, so that's going to change to 3x cubed. This stays positive 6x squared. this one becomes a positive 4x, and then we get a minus 12. So let's take a look at the sign changes. So from here to here, this is one sign change, no sign change, no sign change, but from positive to negative, we get another sign change, so we have 2. Coming back over here, right, again, it's just associated to the f is, so the negative real zeros is either equal to the number of sign changes or is less than the number of sign changes by an even integer. So here it goes. So therefore, we're going to be in the same spot. So there exist either 2 or 0 negative real roots. Okay, and then that's it.